In the previous discussion, I have introduced to you the tree data structure which falls under the nonlinear data structure, and we have seen a special type of tree that is known as the binary tree. So in a binary tree, a node can have maximum 2 children, right? So here you can see a binary tree representation or a binary tree. So 1 is the root, so 1 has 2 children, 2 and 3. Again 3, if you observe, it has 2 children, maximum 2 children, it has 6 and 7. 6 has maximum 2 children, 12 and 13. So in that order, this is a binary tree. So today in this discussion, mainly I will focus on the traversal scheme. That means traversal means I will have to visit all the nodes in a binary tree. So in which order we can visit the nodes in a binary tree. So today I will focus on that part only. Then finally I will show you a sample program for developing the binary tree, and I will show there how in order, pre-order, post-order traversal schemes can be used. Okay, so before going into the details, let us recap how binary tree can be represented. And in my previous discussion already I have gone through the representation scheme. So binary tree can be represented using two scheme. That means one is the array representation, one is the link representation, right? So in array representation, what we have done in the previous class is that if I am having a binary tree, or if you want to represent the tree in an array like structure, then what we'll have to do, first you give the numbering. Okay, so numbering the nodes using the numbering scheme for a full binary tree or a binary tree. The node that is numbered I is stored in the array name is say tree, so in index I it will be stored, right? So if I'm having an array of say size, so for representing this tree, the array size here I am considering as say 11, and the root is numbered from 1. That means in index number 1 we are storing A, index number 2 I am storing B, index number 3 I am storing C, index number 4 I am storing D. So in that order it goes on. So this can be a array representation of the tree like structure for a binary tree. Okay, but there can be different problems may arises while we are representing a binary tree using array. So let us see the problem. So if I am having a right skew binary tree, say after doing some sort of deletion or some sort of operations, if my tree will be look like this, or from the initial phase if my tree is something like that, for representing this right skew binary tree using the array representation, initially how many nodes or how many space I may require, because the depth here, if you observe here, it is 4, right? 1 2 3 4. So what will be the maximum number of elements it may have in the binary tree? It will be 15, because 2 to the power h minus 1, that is the maximum number of nodes which can be present in a binary tree. So for representing this binary tree using the array, the number of element or the number of size of the array also should be the maximum number of nodes which can be present, right? So the size here, as we have started the root from index number 1, so 0th index we are not putting any element, but in 1th index I have put A, in 2 I have putting, because in index number 2 I don't have any element, right? So in the index number 3 I am having B. So similarly we can have in the last index, that means in 15 I am having D. So here you can observe the wastage of space just for representing this right skewed binary tree. Another problem may be here in terms of deletion and insertion operation in a binary, in a array representation. So this is another example for representing a binary tree using array. So this is a left skewed binary tree, this is my array, and this is a complete binary tree which is represented using a array. Though in array representation we may not have the overhead of pointers, but we may have these two problems like wastage of space and insertion and deletion problem. And when the size of the tree is huge, so that time also array representation may not be suitable. So for doing these things, we can go for the link representation, where we will use the structure, and the structure will have 2 pointers. So link representation, here we are considering the nodes as a structure. So if I am having a structure like, say, the name of the structure is a T node, so presently I am considering only, say, one data part in a particular node, say in data. So this can be integer type, and it has 2 parts, one is the left child, one is the right child. That means whenever new node will be generated, it will be attached here. When new node will be generated in the right, it will be attached here, and pointers or the address will be held in a particular node. So we are having integer data, and I am having the 2 pointers of type struct node. So struct node pointer right child, struct node pointer left child. And if you are going to use type def, so T node, so type def can be used here because it is related with the structure. So that can be a scheme. That means we are having data part, we are having left child, we are having right child. Okay, so let us see just a diagrammatic view. So this is A. So it has, for a particular node, presently we are having 3 fields. One is the data part, one is the left, one is the right. So in the data part, presently I am storing A. So A has left child, that is B. So B has left child, that is D. D has left child, that is F. Right? So similarly, A has right child C. C has right child E. So here we are storing the address for this particular node. So here also in the left field, we are storing the address of this particular field. Here also for this node, the address will be stored here. Like in linked list, if you remember, we are having the next pointer. So next pointer is holding the address of the next node, right? So this scheme is powerful, so that can be used for representing a binary tree. So different operations can be performed in a binary tree, like insertion, deletion. So mainly I will focus on the traversal scheme because insertion and deletion can be seen in binary search tree also properly. So binary tree traversal, that means traversal means, traverse a tree means to visit all the nodes in some specified order. Okay, so in binary tree traversal, mainly we are having 3 main scheme. One is known as the in order traversal, one is pre-order, one is post-order. So these schemes can be handled by using the recursion, and the order in which we will have to follow the in order traversal is left, root, then right. So left here means, that means if for a particular node, if I am having left children, then I'll have to go in the left side. If it has right, then I'll have to go right. So that can be the sequence which I'll have to follow. That means left, root, right. So for pre-order, we are having the sequences root, left, then right. And post-order is left, right, root. So in pre and post, you can observe, in pre we are having the root is the initial, and in the post, root is in the last. Okay. And from implementation point of view, we will try to design them using recursive procedures. So with example I will show you, then it will be clear to you. So in order, this is, I am just showing you the, from implementation point of view, this is a function which is written in C++, and also the cout is also shown in printf format also. Like here you can observe, I am having a function called in order. This is the function name, and it is taking the parameter, that means the structure we are passing, and we are passing the root. Okay, root here passing to the function. So if root is not null, then we are calling the function in order again, because the sequence for in order was left, root, then right. So in order we are passing the root left child, then root data we are printing, then root right. That means left, root, right. So that is the sequence we are following here, and recursively we are calling the functions. So this function call means traverse the left subtree of the node in order fashion itself. Then we'll have to visit the root, then this function call means traverse the right subtree of the node in order fashion itself. So let us take an example. So if this is a binary tree is given to you, and if you want to visit all the nodes in order fashion, then what we'll have to do is that first I will check the root. Root is not null, so I'll come to the left branch or the left subtree. Again I will check, is this root is null? No. I'll come here. Is this is null? No. Then I will check for, that means left child. So A do not have any left, so I will print the root. That means for this subtree, this is the root element, right? So A will be printed. Then I will use one term here called the backtrack. Backtrack means I will have to go to the previous state. That means who is the parent of A? That means B. That means this, for A the root is B, right? That means I will have to print B. So that's why the sequence is A, then B. Again I am repeating, first I am coming, I have checked F is not null, then I have come this direction. B again has left subtree, again I have come to A do not have any left child, right? So I have printed A. Then I have backtrack, I have printed the root of A, right? Now this B has left child, because for the B I have gone only through the left branch, then I will have to check for the right. So B has right, then I have come to D, right? Again D has left branch, because I will have to check for the left subtree. Now C do not have any left, so I am printing the root. So C do not have any right, so I will backtrack to D. So I'll print D. So that's why the sequence is A. First I have print A, then B, then C, then D. Okay. Now D has right, so I will come to E. E do not have any left, right? So it will print E, then it will check for the right. E do not have any right, okay, then it will backtrack to D. Then again it will backtrack to B, then it will backtrack to, then F will be printed, because we have started with F has left child, so that's why the root value will be printed for F. Now F has right branch, it will go to Z, okay. Now Z, that means after printing F, it has come to Z, because this is my right branch or the right subtree. Now Z do not have any left subtree or left child, right? So I'll have to print the root, that means the Z will be printed. Now after printing, it will check for the right subtree. So Z has right subtree, it is true, that means I. Now I will check the left, that means it will check for H. H do not have any left, it will print H. H do not have any right branch, okay, so it will backtrack, and finally it will print I. Okay, so that is the sequence which is printed over here. That means, I'll repeat here. So if one node has left subtree or left child, just go deeper. That means F has left, yes. B has left, yes. A do not have any left, so just print A. Okay, then check for right, no right, then backtrack to B. Come to B, print, because for A the parent is B, so I'll have to print B. Then it has come to B has right, it will D, then C. Okay, that means after printing A, B, C, D, E, right? Then F, then G, because Z do not have any left. After Z, it will come to I. So we are not printing I, because I has left subtree or left child. So H is printed. H do not have any right, so it will backtrack, it will print I. So nothing is left here, all the nodes are visited in order fashion. So let us see the pre-order. So in pre-order, the sequence is root, left, then right. So root data means we'll have to print the element, then root left, that means pre-order fashion I will have to call the function itself, then pre-order fashion I will have to call the right subtree here. So let us make the okay. So here with this example you can see a same example I have picked up. So if you want to visit in pre-order traversal, so the sequence is that root, left, then right. Okay, so first I'll have to print this is the root. If root is not null, then I'll have to print root data, that means f will be printed. Okay, then I'll come to the left branch. Now b is not null, so I'll print root, that means b will be printed. Now again I'll come to the left branch as per this. So a is not null, so I'll print a. Then I will backtrack. Then for this b I am having right, so d will be printed. Okay, that means f b a d, f b a d. Okay, now d has left, so c will be printed. Okay, then d has again right, so e will be printed, that means a b a d c e. So this is the sequence we have followed. So now there is no left, no right, so it will backtrack, come to f. The left sub branch of f is already we have visited. Now for root we are having the right branches present again, that means we will have to go to this direction. That means for f has right, that means z. Okay, z do not have any, z will be printed, z do not have any left, so it will check for I. So I will be printed, I has left, then finally h will be printed here. So the sequence will be f b a d c e z I h. Okay, that means root, left, right. So while we are doing the backtracking here, internally in recursive procedures, the stack data structure is used for maintaining the sequence. Okay, so let me recap. That means root is not null, so we'll have to print root. Okay, f. Then this node has left subtree, that means b. So b again we have printed, because first element I'll have to, because the sequence here it is root, left, right. Okay, this one is printed. Now this again has left child, left subtree. Okay, again this is a whole subtree, again consider I will have to print a, that means a b a is printed. Then I will backtrack to b. Now b has right, so I have printed d, then it will check for left. C is printed, now there is no left, no right, so it will come to d to e, it will be printed e. So all the subtree is printed for f, that means we have visited. Now for f the right subtree is left, so we'll have to come to the right subtree. So z is printed, then I, then h. Okay, now in post order, so root will be printed in the last. Okay, that means left, right, root. So I'll come to f. F has left, f b has left. Okay, so I'll print a. Then a is printed, it will come to b. Okay, now it will check for the right. Now this one is again has left. Okay, so it will be printed c, right. Then d has right, so e will be printed. So after printing e, left and right sub all are visited, so it will print the, for c and e, the root element here it is d, so d will be printed. Then a is visited, d is visited, now we'll have to print b. So that's why the sequence is initially it is a, then c, then e, then d, then b. Okay, now we are not going to print f, because for f only we have left subtree is only visited, so we cannot print f. So I'll have to go to the right subtree of f. Okay, now z, now it will check for left, there is no left, so I cannot print z, I'll have to check for I. I has left subtree, that is h. H do not has left, h do not have right, so we are going to print h. Okay, then it will come to I do not have right, so I can print now I. That means after printing h, it will print I. Then for z, left already we have visited, that means there is no left, that's why we have come to right direction. Now this part is done, so I can print z. Now for f, all the left and right is visited, so finally we can print f. So that's why the sequence is, first we have A, then C, then E, D, B, right? Then we have print H, then I, then G, then F. So that is the sequence which is followed here for the post order traversal. So let us see another example. Say this is a binary tree which is given to you. Now if you want to follow the sequences like pre-order, in order, or say post order. So in pre-order the sequence was root, left, right. Is not it? So we'll have to, in pre-order, root, left, right. So root, then again left branch, it is be printed 5, then 9, right? Then I'll come here, 7 will be printed, then 1, then 12, then 2, right? Then I'll go, then next will be printed 4, then 11, then 3. Now in order traversal the sequence was left, root, right. So I'll come down, deeper, 9, that means left, then so it has no left, so I'll print 9, then 5, then 7, that means after 9 I will come to 5, then 7 has left, that means 1, after printing 1 it will be 7, then it will come here, then come here, 2 will be printed, then it will print its parent, that is 12, then it will go, it will be 8, then 4, then 3, then 11. So similarly post order also we can have this sequence like 9, 1, 2. In post order we are having the sequence called left, right, root. So this can be the sequence we can observe in post order. So you can see in pre-order the root is always in the first position, and in post order the root is in the last, it is printed. So this is another example. So this example I am going to input to the program, then we will verify this binary tree with the sequences. Okay, I hope the traversal schemes are okay with you. Now let us see the implementation code for representing the binary tree. So this is the program. Here you can observe, like I am declaring a structure, that is a struct node. It has the data field and it has 2 pointer, the right child and left child. Struct node pointer right, struct node pointer left. Okay, then I have wrote the function calls a create binary tree, and this create binary tree is going to create a binary tree, and it is the return type of this create binary tree is the struct node pointer, because after representing or after creating the tree we are going to return the root. So I will come to this function. Let us see first. Then here is the in order function, in order, and in the slide also I have shown you that means we'll have to pass the root as a parameter. So if root not null, so something like that. Then in pre-order we are having the sequence, say root left, right, then post order, which I have already shown in the slide. So that same code is used here. So these are the three schemes I have shown, and this is the main function. So in main function, so one variable of type structure node is created, struct node pointer root. Then the function create bt is called. That means this is the function create bt. That means this is the main function for creating the binary tree, and the return type here it is struct node pointer, because the function is going to return the root. Okay, so this function is called and it is in the root. Then this is the printf statement, that means for printing the traversal. the in order traversal of binary tree, then I have called the in order function and I have passed the root as a parameter. Similarly for pre-order, I have called the pre-order and I have passed root. Then for printing in post order, I have root is passed here. Now see the main function, that means the create binary tree. So this is a very simple function. So just for representing the null values, that means if the user, because I am going to consider only say integer data here, only some number will be inputted into the tree. That means say printf enter the data. So from user side I will input some values. So suppose if the user has input say -999, so it will represent null values there. Okay, just to represent this null. So if user has not inputted something like that, so that time what I will do, I will create struct node pointer. That means dynamically node will be generated, because this is the link representation using the dynamic representation. So after creating the node, the whatever the say I have inputted say 100, so 100 is not equivalent to -999, so I will not going to put null there. So this 100 will be stored in the t data part. Then I will ask to the program, that means enter, I will ask the user, that means enter the left child. Then again the user will input the left child, and it is also a recursive procedure, so it will again call the function itself, create bt in the left direction. Similarly if you want to insert in the right, then I will call the function create bt in the right child. Okay, then after inputting all the values, finally I will have to return the root, because I need the root. That means the root address should have to be passed to the function. So let us execute the program. So let us input these values itself to be more clear. That means here 500, 300, 400, something like that, is not it? So first I'll input say 500. So enter the left child of 500. So left child of 500 here it is 300, right? So 300 is inserted. So enter the left child of 300. So in the diagram, if you observe, for 300 there is no left child, it is null, right? So for representing null, what value I will have to input? -999. Now the program is asking enter the right child. That means a right child is 200. Okay, so let me place it. Okay, so 300, now I'll have to input 200. Okay, now for 200 it is null, it is null. So what I'll have to do, left child I'll have to print null null. That means 999 I'll have to input. For right child also I'll have to put this. Okay, so this is done. Then I will come to 500. Then for 500 left branch is done. Now it will come to 400. Okay, I'll have to input 400 because right child of 500 as per this example it is 400, right? Now left child of 400, yes, it has left child, that means it is 100. Now left child of 100 is null, right child of 100 is null. So I'll have to, for null I am putting 999, and for right child also 999. Now what is the right child of 400? Again is this 999 because it is null. So my tree is constructed. If I'll press enter, automatically this traversal sequence will be shown. So let me press enter and I will see whether the tree is constructed or not. If this sequence will come, that means I can verify, that means my tree is constructed, and the traversal sequence is also proper. So let me enlarge it. So you can verify here, that means the in order traversal of binary tree, that means 300, 200, 500, 100 and 400, right? The pre-order is 500, 300, 200, 400 and 100. Similarly for post order, the outcome is 200, 300, 100, 400 and 500, right? So manually also, if you want to verify here, that means in order traversal, that means left 300, right? 300 will be print, then it will be 200, then it will come to 500, right? Then it will come this, then 100 will be printed, then 400. So similarly we can verify the pre-order and post-order for this small tree. Okay, so this is the program output, and the program is correct, and we have verified it using the traversal scheme. So again I am repeating, this is the function create binary tree. It is the return type is struct node pointer because it is going to return the root. So first we are creating a node, and in the node we are just inserting the values. Then if you want to insert some element in the left child, just call the function create bt. If you want to insert in the right, just call the function create bt. For inserting the null values, I am just using 999 here. And finally after generating, it is calling the, it is returning the root, that means the t. Okay, so if possible, try to design this program using C++ concept also, then it will be clear to you. So in today's discussion, I have mainly focused on the traversal scheme. Also I have shown you as a recap the representation of the binary tree in computer memory, and also lastly I have shown you the implementation of the binary tree. In the next lecture I will discuss a very special type of binary tree which is highly used, that is known as the binary search tree. And I hope into this lecture you have understood the traversal sequence, in order, pre-order and post-order. There is another traversal scheme is also present, that is known as level wise also. In level wise, just as example, I will just highlight. In level wise traversal, that means in level wise you will have to visit, that means the level of 8 here it is 0, right? Then 1, this is 2, this is 3, this is 4, that means up to 4th level this binary tree is generated. So in the first level the element here it is 8 will be printed. Then in the next level, that means in the 1th level, 5 and 4 will be printed, that means in sequence. Then 9 will be printed, 7 will be printed, 11 will be printed, then 1 will be printed, 12, then 3, then finally 2. So there is another scheme that is also can be used for tree traversal, that is known as the level wise traversal. And level wise traversal is mainly used in, I will discuss, that is known as the BFS, breadth first search, while I will discuss about graph data structure. But mainly we will focus on this tree traversal scheme, that is the in order, pre-order and post-order. So thank you very much.